All right, so we're going to now talk about the 4 different types of structural elements. So these 4 types, it's important to kind of understand how they build off of each other. So the most fundamental, kind of easy to wrap your hand around type is just a beam. And when I say arbitrarily curved, that basically means these beams are made of linear segments connected by nodes. So typically in application, your beam will be straight, but you can make curved beams with a number of segments connected by nodes. Bisymmetrical cross section. The material is elastic, and you can introduce plastic hinges. So a lot of times when we're talking about structural elements, we're going to distinguish elastic elements versus plastic elements. Now, plasticity is a very important part of finite elements, any finite element code. But right now in FLAC2D, we do not have plasticity for these structural elements. You do in 3D, but that logic has not been ported over yet. In fact, I'm doing that right now. So what we did instead was, it was a lot of our consultants needed a way for these beams to behave plastically instead of just perfectly elastic every time. So we introduced this idea of a plastic hinge where once it reaches the bending moment of some sort of bending strength, the node will behave plastically and just start bending in a plastic manner. It's not true plasticity, because if you're bending a steel bar and it becomes plastic, that plastic range is actually starts at the middle and then comes down, or basically the plasticity there with the drive. Okay, so beam is the most simple structural element in FLAC2D. And right now, I don't have it listed here, but I'll talk about how beams interact with the grid in a little bit. The idea is that you have these elements that have also they respond to forces in a certain way. And then you also have the way they interact with the grid, which is distinct from how that element behaves. That distinction is important, and I'll try in the next slide. I'll hit on that more. So piles basically are like a beam, but now instead of just having all the functionality of a beam, they also have frictional and cohesive interaction with the grid. Much like I assume we all know what piles are. You're pounding a pile in soil. The way it interacts with the grid in shear and in the normal direction can be modeled. Frictional and cohesive in both directions. Also piles, got piles shoved into the ground, you're laterally loaded. It can actually create gaps that can open and close depending on the loading. And I have all these little links here, and instead of going to each link, I'm just going to leave the links in there for your convenience. So if you're ever going through this presentation, you can just click on it and see the actual in-depth explanation of all these element types. All right, so liners. There's a lot of confusion with liners. What we're trying to reinforce with liners is that they are modeled as a beam, but they are continuous out of the plane of analysis. And we'll talk a little bit more about how that's done. It's actually pretty simple, but the idea of liners is that they're always continuous. They're not these, they don't form in an array out of plane like beams and piles do. Their interaction with the grid is much like a pile. However, they have subtle differences in how they interact in the normal direction. And those subtle differences are basically to really mimic what a concrete liner might be. And like the interaction with the grid for piles is very similar to how a pile might interact in real life. All right, so beams, piles, and liners are all very similar in how the element itself responds to forces. They're very different in how they interact with the grid. Cables are different in the fact they are strictly 1D elements. Basically, they can not resist any bending moment. It's basically like a string, except for it's a cable. They can yield in tension and compression. They're used a lot in applications for soil reinforcement. And then the way they interact with the grid is everything is specified as a grout. So you can specify grout properties for the cable. And that will add another dimension of strength and flexibility for these cables. And then rock bolts. This is basically something that was added later to piles. It's an extension of piles. It basically gives the pile the ability of a cable. So just a straight pile cannot yield in the axial direction, but rock bolts can. And so everything that a pile can do, a rock bolt can do. And then rock bolts also give the piles the ability to yield. So they're commonly used in tunnel reinforcement and that kind of thing. So obviously this is 5 types, but really rock bolts are just more of a pile with additional features. Okay, so I'm just trying to really hit home here that when it comes to structural elements, there's two different ways these things respond. One is how the element responds itself, and then the other way is how it responds by interacting with the grid. In this grid interaction, I'll use the word a lot: linking, or coupling. It means the same exact thing. So I kind of talked about the element response. Beams are elastic material with no failure limit. Piles are the same as beams. Liners are the same as beams. What really differentiates these types is how they interact with the grid. So beams are always rigidly connected in both the shear and normal direction. Ideally, a beam, and I don't know if I've ever seen a beam used for any other application, is other than support in the trench. Trench. Do this all the time in civil engineering. Beams come across supporting the load of the soil. So these interaction, the interaction there is rigid. And it has no deformation laws. It has no cohesion, no friction, anything like that. It's just a rigid attachment. Piles, on the other hand, now we're talking about the interaction with the grid in the normal shear direction can have friction and cohesion, and stiffness. And we'll talk about kind of how you determine what those quantities might be. Stiffness between the element and the grid, the zones, isn't just something that you can look up in a handbook and find that value. So we'll talk a little bit about how these quantities are calculated. So the liner is one step further from the pile, very similar, but again, the grid interaction in the normal direction, right here, both compressive and tensile forces can be carried. And then lastly, the cable is basically, it's all a shear directed thing. Everything to do with the cable is only in shear.